everyone, Dr. Tullis here, picking up lessons from where we left off. This time we're investigating the third law of thermodynamics, and in this investigation we will be studying the entropy of a pure, perfect crystalline substance assigned 0 Kelvin, which we know to be absolute zero. So the third law of thermodynamics, pure, perfect crystalline solid, absolute zero, which is Kelvin, 0 Kelvin, which we know that nothing is colder. All molecular motion would stop, and therefore there's no molecular motion. Entropy is assigned 0 for all perfect crystalline substances. Of course, these are theoretical substances because we've never achieved absolute zero. What we do is we make careful measurements to determine the temperature dependence of a substance's entropy, and then simply derive these values under specific conditions. Standard entropies, which are given the symbol with the sub-naught superscript, and we measure those at 298 Kelvin, which we know is standard temperature, 25 degrees Celsius, and at 1 atmosphere of pressure. We call those standard temperature pressure values. So that's our entropy sub-naught at 298 Kelvin, which is 25 degrees Celsius, and at 1 atmosphere. And again, we call this STP, or standard temperature and pressure values. And again, this is called absolute zero. So the S sub naught is a standard temperature and pressure values. So these values are determined for 1 mole of a substance at 1 atmosphere and 298 Kelvin. What we can do is then compare the entropy change from that pure crystalline substance at 0 Kelvin to the 25 Celsius or the 298 Kelvin species. And those values are computed and placed into the standardized charts, which are in our appendix of our book. And you can find those thermodynamic qualities there. Just like we had in our last chapter when we were calculating enthalpy of a reaction of the system, and you would look at the sum of the products minus the reactants. When we would look at the sum, when we would look at delta H for the reaction, which was equal to the sum of the products minus the sum of the reactants. Do you see how these standard states are used in the same way for entropy? Remember that when we are calculating the delta H, the enthalpy of the reaction or the entropy of the reaction, and we are doing products minus reactants, it's the sum of those products, and it is coefficient dependent when we calculate those values. So these standard entropies, this little symbol here, means that the standard conditions, which is 298 Kelvin and 1 atmosphere pressure, if you happen to have an aqueous solution, it's 1 molar concentration for standard conditions. And to calculate the standard entropy change as reactants turn to products, we look up each value in our appendix in the thermodynamics chart, and we take the sum of the products minus the sum of the reactants. So here are some standard molar entropy values pulled from the appendix, again, from the back of the book or notes that you were given, where you're given the elements or the compounds, and we're able to see these entropy values. Again, remember that the standard molar entropy of a substance is the entropy gained by converting 1 mole of it from a perfect crystalline solid or whatever the state that it is at 0 Kelvin to standard state conditions. And so again, one thing to notice is that every one of these values is positive. And that's because every one of these values, again, we're going from 0 Kelvin, which is theoretical, which should be zero movement, to raising that temperature where there is chaos and disorder. So every one of these values is going to be a positive entropy value. So this critical observation is reminding us that the third law of thermodynamics would say that every pure crystalline substance would have a value for entropy of 0 joules per Kelvin mole. That's its assigned value. So if that is the entropy, it's not just change, it's got to warm up, right? So it's going to be a positive value. It will gain kinetic energy through thermal energy and vibrations and so forth. So entropy values are always written as positive values here. So if we were to look at graphite, we see carbon in graphite form is 5.6. Carbon in diamond form, 2.3. Carbon vapor, 158. So we know to go from graphite form to gaseous carbon, it's going to take a lot. It's a lot more disorder, right? Let's look at fluorine and chlorine gas, 202 versus 223. So there are some observations we can make that as we go down a group or a family, that as we get bigger, more massive particles, that chaos or disorder increases. We can also look at, here we go, some compounds. Ethane, methane, ethane, propane. And we can see 186 to 229 to 270. So again, as those compounds get bigger, that and more massive and more complex, that the entropy increases for those compounds. We can also see that water as a gas compared to water as a liquid. We can see liquid was 69 and gas was substantially higher. Again, as our entropy, as chaos goes from a liquid to a gas, entropy is going to be positive. It's going to increase. Let's take a look at an example problem. So let's consider the reaction of hydrogen and oxygen to form liquid water. So let's write this reaction out. We have hydrogen and oxygen to form liquid water. Let's balance our equation here. We need two H2s for two H2Os. That should be good. We know that these are gaseous, and we know that that's a liquid. All right, so now this table tells us this is our thermodynamic properties table, where we have our enthalpy, again, that's kilojoules per mole. This gives us free energy, which is kilojoules per mole, and our entropy values, which is joules per mole Kelvin. So these are important things to note. So again, this is delta H, this is delta G, and this one is, wait a second. Oh, I need to shift it one over. Sorry. This is our substance here. This is our delta H, delta G, delta S. And again, remember our delta S is in joules per Kelvin mole. And both of these are in kilojoules per mole. So that's important to note. Now, we need to figure out what our entropy, what is the standard molar entropy for this reaction. So we want to find out our delta S. Now let's make a prediction. We're going from gas to liquid. So gas to liquid, is that becoming more organized or more dispersed? Well, we're going from gas, which is crazy, very dispersed, to more organized. So I'm going to make a prediction that our delta S is going to be negative. Now, remember to do this to find our delta S for the reaction. We need to do the sum of our products minus the sum of our reactants. And to do that, we're just going to plug in the values that were given from this table. So let's look at our products. We have 2 moles of liquid water. So we're going to do 2 times, here's our liquid water, and here's our delta S for it, 70. 70 joules per Kelvin mole. Those are my my products. Products minus, let's do our reactants. We have 2 moles of H2, so we're going to do 2 times, here's my H2, 130.7, plus 1 mole of O2. There's my O2, and I'm just going to do, so 1 mole of 205.2. These are my reactants. Okay, so now let's do some calculator work. I'm going to do 2 times 70, right, let's do 140, duh, minus, I'm going to do 2 times 130.7 plus 205.2. So I have 140 minus 466.6. So 140 minus, my answer I just found, we have negative 326.6, and this is joules per Kelvin mole. And this is my delta S for the reaction. And if we think about it, I did predict that I would have a negative value because, again, I am becoming more organized. Let's look at another example problem. We want to calculate the standard entropy change for the following reaction at 25 degrees Celsius, as values can be found here. So we've got propane, so we've got a combustion reaction here. Propane plus oxygen gives me carbon dioxide and water gas. Okay, so these values would always be provided to you, whether it was a test or a quiz or whatever. So we need to find, here we go, our delta S is equal to, remember, the sum of our products minus the sum of our reactants. So let's look at our products first. We've got 3 moles of CO2 gas. So let's do 3 moles of CO2 gas. Our entropy is 213.8. And we have 4 moles of H2O gas. H2O gas, 188.8. These are my products. And you know what? We don't have much room over here. So let's find our products first, and then we will find our reactants, and then we will put it all together. So let's do 3 times 213.8. And let's add 4 times 188.8. So we have a products total of 1396.6. Okay, this is my products. Now let's look at our reactants. So I'm just going to do a little, this is my products. Okay, now let's do minus our reactants. We have 1 mole of propane. So we'll do 1 times 270.3 plus 5 moles of oxygen gas, 205.2. All right, let's do this math. So we have 270.3 plus, so 270.3 plus, I'm going to do 5 times 205.2. Now reactants, we should have 1296.3. So now let's plug it in and do products minus reactants up here, 1296.3. Let's get our total. 1396.6 minus 1296.3. And we have a delta S for our reaction, our total entropy for the reaction is equal to 100.3 joules per Kelvin mole. And this is a positive number. And so let's think about it. If we look at all of our reactants, all of our products are gases. And if we look at this, I have 1 mole of gas plus 5 moles of gas. I have 6 moles of gas producing 3 plus 4 moles of gas. That's 7 moles of gas. So I went from 6 moles to 7 moles. So I expanded. So I have a positive entropy. Having more particles, that means having more microstates. So we just have more chaos in our system, giving us that positive value. So here's an example of an old test question. At 298.15 Kelvin, all the following substances have standard free energy of formation of 0 except who? Now, if we notice when we're looking at our thermodynamic properties chart, and we're looking at enthalpy and gives us free energy values, that the substances have zeros, and we talked about this last unit, if they're in the state that they are found in naturally. So aluminum, solid aluminum, has enthalpy of 0 and free energy of 0. So what this question is really asking is which element is not found in nature as stated? So is it gaseous bromine, solid iodine, rhombic sulfur, chlorine, gaseous chlorine, or liquid mercury? So we would need to look at our thermodynamic properties chart to see, well, which one is not natural. And we would find that bromine is not found as a gaseous substance in nature. It's actually found as a liquid. Bromine, Br2, and mercury are the only 2 elements that are liquid in their natural state on the periodic table. And so for liquid bromine to turn into gaseous bromine, if we looked up gaseous bromine on our thermodynamics chart, we would see that it is a positive value, that it takes energy to go from the natural liquid state to the gaseous state. Let's look at another example, pulling in the 3rd law of thermodynamics, as we calculate the standard entropy change for the process of the evaporation of ethanol. So you would need to know that evaporation is going from a liquid to a gas. So we would take a guess, is this going to be a positive or a negative value? Going from a liquid to a gas, if we're looking at entropy. Well, it should be a positive because we're going to more disorder. So looking up on our thermodynamics chart, we can find the entropy value of C2H5OH, of our ethanol, in liquid form and in gaseous form. So then to find as for our system, or the system is another system or reaction, can be used interchangeably. We just do our products minus reactants, and we have 1 mole of each. So we're just going to do 282.7. This is our joules per Kelvin mole. Products minus reactants, 160.7. And we should get, if we do our calculator work, 282.7 minus 160.7. We should get positive, notice that's a positive number, 122 joules per Kelvin mole. And this should make sense. Again, we're going from a liquid to a gas, so we have more disorder. So now we're going to take a look at going back to the second law of thermodynamics and kind of integrate that with the first law of thermodynamics, where we learned that the first law of thermodynamics is the total amount of energy in the universe is the sum of heat and work. And we defined the system and the surroundings in that process as well. We defined the entropy of the system to be related to the heat with which is Q divided by temperature. And the temperature is in Kelvin to give us joules per Kelvin. We also looked at the entropy of the surroundings as being the heat from the surroundings divided by that temperature in Kelvin. Also giving us a joules per Kelvin unit. Then we can go and we can say, well, the heat of the system plus the heat of the surroundings is equal to 0. And then if we just rearrange this equation, so let's say I subtract Q surroundings from both sides, I would have the heat of the system is equal to the opposite of the heat of the surroundings. So then we can rearrange this even further. We can say, well, the heat of the system is then equal to the change in enthalpy of the system. So therefore, the Q of the surroundings is equal to the opposite of the enthalpy of the system. And therefore, and this is the important one, the one that we need to memorize and know for testing purposes. I'd like to know how to calculate the entropy of the surroundings. And to do so, I need to use the heat of the reaction of the system divided by the Kelvin temperature. So this is the enthalpy change of the reaction. Now, let's be clear. On the last slides, we've been saying the entropy of reaction is equal to the sum of the products minus the sum of the reactants. That's what we were just playing around with, and that is in this reaction is what we call the system. Sum of the entropy change of the reactants minus the sum of the entropy change of the products. But if I want to know the entropy change of the surroundings, I use the enthalpy change, and notice the negative sign because that's an important part here. The enthalpy change of the heat of reaction over the Kelvin temperature will give us that delta H, that enthalpy heat of reaction. And of course, we also remember that the entropy of the universe is simply the sum of the system and surroundings. So here's everything that I was just saying. The entropy of the reaction or the system, same thing. What we were just doing was the sum of the products minus the sum of the reactants. The entropy of the surroundings, right here, is the opposite of the enthalpy of the reaction over temperature. Remember that the entropy of the universe is equal to the system and the surroundings. So we can indirectly measure the surroundings, knowing that they give us the total amount of entropy change in the universe. All right, let's look at an example here. Let's say that I have aluminum plus oxygen to create 2 moles of aluminum oxide. And we're given the delta H of our reaction. We're also given some values here. We know that this is our delta H, this is our delta G, and this is our delta S. Okay. So we want to find the standard entropy values for the delta S of the system or the reaction. So again, for the system or the reaction, think of the whole reaction, we're going to do products minus reactants. So we're using this column right here. We're going to do products. So we're going to do delta S for the system or reaction, either one, same. They're the same terms here. So we're going to do the sum of the products. I should put the S right there, the sum of entropy of the products minus the sum of the entropy of the reactants. So let's do that. We've got our products would be 2 times our aluminum oxide, 50.9. And that's joules per Kelvin mole. So that's our products minus our reactants. I have 4 times my aluminum, which is 28.3, plus, put that in reference, 3 times my oxygen value, which is 205.2. So let's do some calculator work here. 2 times 50.9, 101.8 minus, all right, let's do this whole chunk. We have 4 times 28.3. We're going to add that to 3 times 205.2. I got 728.8. So let's do 101.8 minus my answer that I got. You should get negative 627 joules per Kelvin mole. And that was my delta S from my reaction or my system. So we're going to plug that in here, negative 627 joules per Kelvin mole. Now, let's calculate the delta S of the surroundings. And the surroundings is when we do the opposite of delta H of the reaction divided by the temperature in Kelvin. So to do this, we let's set this up, delta S for our surroundings equal to the opposite of delta H for the reaction over temp. So to set this up, we are going to just look right up here where we're given our delta H for the reaction, negative 3351.4. So we got to do the opposite of negative 3351.4. Now this is in kilojoules per mole. Now when we add up our reaction and our surroundings, we need them to be in the same unit, and we need them to be, to find our delta S, we need it to be in joules, and this H is in kilojoules. So let's just right off the bat change this to joules. We know that for every 1 kilojoule, there's 1,000 joules. So we'll just do that right off the bat. And then we'll divide it by our Kelvin temperature. It told us right up here is 298 Kelvin. All right, so let's do some math here. Negative 3351.4, we're just going to times it by 1,000. And then remember, it's the opposite of that, so we're going to make that a positive. The opposite of a negative is going to be positive, so I'm just going to write in 3351,400. We're going to divide that by our 298 Kelvin. So our delta S for the surroundings is equal to 11246.3 joules per Kelvin. And we're going to plug that in up here, 11246.3. Notice that's joules per Kelvin. And then finally, to get our entropy of the universe, we're just going to sum the two together. So we're simply going to take our entropy of the reaction, which is our products, minus our reactants, where we got negative 627. And we're going to add it to the entropy of the surroundings, 11246.3. And we get a total of, let's clear this up, negative 627 plus 11246.3. And we should get 10619.3 joules per Kelvin. Nice work. I know that was a lot. So I want you to try one on your own. So why don't you pause the video and see if you can consider this reaction going from graphite, carbon graphite, adding chlorine gas to get carbon tetrachloride in liquid form. We're given the delta H of the reaction. Can you find the entropy of the system, the entropy of the surroundings, and the entropy of the universe given this data here? So pause the video and let's see what you can get. All right, let's take a look at what we've got. So let's look at our delta S for the system. And we're going to call it our reaction. We're doing our products minus our reactants. So we've got 1 carbon tetrachloride. So I'm going to find carbon tetrachloride, and we're going to do 214.4. Again, this is our joules per Kelvin mole. So there's our products minus our reactants. Now our reactants, we have carbon over here, and carbon is 5.7. Minus, I'm sorry, we got to add all of our products. We have 2 chlorines. Where is chlorine? Chlorine's right here. 2 times 223.1. All right, and this is our reactants. So our delta S for the reaction, when we do our products minus our reactants, given our entropy values from our thermodynamics chart, we're going to do, let's see here, 5.7 plus 2 times 223.1. And then I'm going to do 214 minus that answer. And I got an entropy value of negative 237.5 joules per Kelvin. And if we think about this, does it make sense? We did go from a gaseous substance to a liquid. So going from a gas to a liquid, we're becoming more organized. So a negative value would make sense. So negative 237.5. Okay, now let's look at the surroundings. So our negative delta H, which was negative 139 kilojoules, let's just put it right into joules right off the bat. And remember that there's 1,000 joules in 1 kilojoule. So let's just make this negative 139,000. Instead of kilojoules, we're just going to make it joules. And We're going to put that over our temperature of 298 Kelvin. So that will give us joules per Kelvin. So a negative and a negative becomes positive. So I'm going to do 139,000 divided by 298. And I've got 466.4. This is joules per Kelvin for our surroundings. And then to find our delta S for the universe, we're just going to sum the two together. So negative 237.5 joules per Kelvin plus 466.4 joules per Kelvin. And we get a grand total of negative 237.5 plus 466.4. 228.9. So that's a positive value. And if we think about this, a positive value means that it is our S of the universe is it's becoming more disorganized. For the universe is becoming more disorganized as a whole. And our delta S for the universe, if it's greater than 0, is telling us that we have a spontaneous reaction. Remember, if our delta S is less than 0, that it is non-spontaneous. So this would be telling us that this is a spontaneous reaction in nature. Here's a question that's asking us to calculate the entropy of fusion and the entropy of vaporization for lithium. And this is a homework problem. But so we're focusing on lithium here. Here's our delta H of fusion. Here's our enthalpy of vaporization. And we're given the temperature at which the heat enthalpy of fusion happens and of vaporization. So it wants us to find these values. And notice that it gives us the unit that it wants it in, which is in joules per, and then this -1 and -1 means that it's the inverse, so we have joules per Kelvin mole. Okay, so if we look up here, we see that our enthalpy of fusion, the heat of fusion, is in kilojoules per mole. So if I were to write down this 2.99 kilojoules per mole, we're halfway to the units that it wants. Here's what we want to get to. If we have kilojoules, we can get to joules, can't we? We can just multiply by 1,000 because there's 1,000 joules for every 1 kilojoule. So the kilojoules would cancel out. So now we're left at joules per mole. I just need to have Kelvin on the bottom. And look, we have Kelvin right here. We can put on the bottom 454 Kelvin. Now we have joules per Kelvin mole. All we're doing was manipulating what we were given to get to the answer that it asked for. So essentially, to find this entropy of fusion here, we did delta H times 1,000 divided by the temperature. So let's do this math out to see what we get. 2.99 times 1,000. Oh, I only did it by 100. 2.99 times 1,000. I was going to say that doesn't look right. And divide it by 454. So I got a delta S of 6.59 joules per kilogram, or joules per Kelvin mole. And then if we go over here and look at the entropy of vaporization, again, we want the same units, joules per Kelvin mole. We're given kilojoules per mole. So let's just take this delta H of vaporization, this 134.7 kilojoules per mole. Let's times this by 1,000 so we can get rid of kilojoules. get rid of those kilojoules, and divided by the temperature at which the heat of vaporization happens, 1615 Kelvin. So then we have Kelvin mole on the bottom. So let's do 134.7 times 1,000, then divided by 1615. So then we have delta S is equal to 83.4 vaporization, 83.4 joules per Kelvin mole. If you think about it, remember delta S, looking at our entropy, is our disorder in the system. And if we're looking at fusion, heat of fusion, right? This is happening when we're going from solid to liquid. That disorder compared to vaporization, we're going from liquid to gas. Obviously, this is going to be substantially more disorder, more chaos in the system. So it makes sense that this is a much larger number. Let's look at this chart. So we're going to look at the different phase changes and look at the system's delta H and delta S. So remember, delta H, we have our enthalpy. And our delta S, we have our entropy. Okay, so let's look at this graph here. If I have temperature on the bottom, and over here I have entropy. All right, so let's say that we have a solid here. And as temperature rises, entropy increases. Kinetic energy is increasing, right, as temperature rises. And then we hit the melting point where we have solid to a liquid. This is our melting. Solid to liquid melting. Now temperature stays the same here, but entropy still increases. And then once all of that solid has melted, temperature rises, and we now purely just have liquid. All right, so temperature is rising, entropy is increasing still. And then we hit the boiling point where we convert phase change, liquid to gas. Entropy increases, temperature is not, right? It does not increase until all of that liquid is turned to a gas, and then temperature increases when we are purely in gas form. So when we are going in this direction, this is endothermic, right? We are absorbing heat energy to make this happen. And as we are doing that, entropy is increasing. Now, if we go in the opposite direction, that is our exothermic. When we are releasing heat energy to go from a gas to a liquid, we have to get rid of energy to do that. So if we look at this, when we have positive delta H and positive S is our entropy. Positive S is when we're going from a solid to a liquid to a gas. So our solid to liquid, liquid to gas. We're going from a solid directly to a gas, or sublimation. So what we're seeing here is that when delta H is positive and we have an endothermic reaction, and when delta S is positive and we have more disorganized system, that we have more microstates, that we have more chaos in the system, that these two go hand in hand together. When we have a positive delta H, we have a positive S. And we can also look at the opposite direction, exothermic. So delta H is negative when we have exothermic, and we have delta S is negative where we're becoming more organized. So when we're going from a gas to a liquid, when we go from a liquid to a solid, these are exothermic. It's releasing energy to go from a gas to a liquid to a solid. We're becoming more organized. Gas to a liquid, liquid to a solid, and deposition when we go from a gas to a solid. Again, releasing heat energy, exothermic, and becoming more organized. So these are just some examples of phase changes where we can look at enthalpy and entropy and the relationships of the two of those. And interestingly, when we're looking at phase changes, there aren't any examples of having an endothermic reaction that's becoming more chaotic, or that, I'm sorry, an endothermic reaction that's becoming more organized, or an exothermic reaction that is becoming disorganized. So that doesn't happen in our phase changes, but a good way to put together our delta H and delta S for phase changes.